I'm Rachel Sinclair, an electrical engineering student.
My name is Tyler Mills. My major is optical science and engineering.
I'm Gavin Mitchell, and I'm an electrical and computer engineering major.
My name is Ricardo Padilla-Vera. I'm a mechanical engineering major.
My name is Bridget Slomka, and I'm a biomedical engineering major.
I'm Daniel Taylor, and I'm a mechanical engineering student.
And we are CycleSafe. In 2018, 857 cyclists were killed in collisions with vehicles, and thousands more were injured. This is a 6% increase from the year before. To combat this, there is an Arizona state law that mandates when passing a cyclist, a vehicle must give at least 3 feet of passing distance until they've completely overtaken the cyclist. This law is not widely known and is rarely enforced. Because of this, Dr. Daniel Latt proposed a low-profile proximity sensing, warning, and reporting device that goes into the left handlebar of the bicycle. This project is important to all of us in the team who bike to school every day and have all had our share of close encounters. On behalf of the team, it is my pleasure to introduce CycleSafe, our patent-pending technology.
The idea behind CycleSafe was to create a device intended for any level of cyclist that delivers big results in a small package.
CycleSafe is intended to fit largely within the left handlebar of a standard road bicycle, with minimal protrusion to conserve aerodynamics and aesthetic appeal. It effectively replaces the left handlebar end cap, but adds multiple features.
To take advantage of its placement on the left periphery of the bicycle, CycleSafe is outfitted with 3 red LEDs facing the rear that consistently flash at 1 Hz to indicate the presence of the cyclist to motorists coming from behind.
Next, our device serves to alert motorists when they breach the mandated 3-foot radius. CycleSafe employs an ultrasonic sensor to detect vehicles within 3 feet, after which it illuminates a side-facing LED to flash at 4 Hz, informing the driver of their proximity.
Finally, the device has a forward-facing camera that serves to capture license plate images of vehicles that violate the 3-foot passing law. These images are then saved to an SD card and can be sent to law enforcement to increase driver awareness.
The main components of our system are a microprocessor, a camera, an ultrasonic sensor, rear-facing LEDs, side-facing warning LED, an SD card system, an on and off switch, and a battery.
Our system was adapted using open-source software and is wired as shown. It's been implemented using both the Arduino Nano and Uno microprocessors with plans for the next version to use the Atto, the world's smallest Arduino-compatible microprocessor. As you can see, when an object passes within 3 feet of the device, a warning LED begins to blink and the camera takes a picture every 50 milliseconds for 4.5 seconds.
The 2 main criteria for selecting our camera were Arduino compatibility and the actual dimensions of the camera module itself. We wanted the portion of the system which protruded from the handlebars to be minimal so that we could avoid causing imbalance for the cyclist. The optical specifications of the camera, of course, were also important. Particularly, we had to ensure that the pixel size of the sensor we were using would provide legible images of the license plate characters all the way up through our maximum operating distance of 14 feet. So using Gaussian imaging equations, I was able to plot the pixel size of the sensor against the number of pixels which would cover a given license plate character. We used this plot in our trade study along with pixel coverage recommendations sourced from license plate imaging literature. After finishing the trade study, we decided on the 2 and 5 megapixel ArduCam modules. Test images from these modules can be seen here.
The main goals when creating the design of the device were to have it fit within a bicycle handlebar and maintain a light and small form while also being resistant to damage. The casing of the device was split into 4 separate pieces to allow for easier assembly of the inner components. The 4 different pieces that make up the casing include the front cap, which has an on and off power button along with 3 rear-facing red LEDs. The front cap also houses a micro SD card reader, a micro USB charging port, and the back portion of the device is mountable within a bicycle handlebar. The side housing houses the ArduCam camera, a side warning LED, and the ultrasonic sensor. The final piece of the device is an end cap, which holds all the components together.
For our current 3D printed prototype, we use PLA filament and recommend in the future versions to use nylon due to its durability.
It is important to note that all inner electrical components are fastened using a protective foam and an adhesive. The device is mounted within a handlebar using a compression fit. It is always mounted in the left handlebar to ensure that the camera is always facing the road. A simple power analysis was conducted by looking at the capacity of the battery and the current draw of each component. It was determined that the device would last roughly 8 hours and 45 minutes under constant operation.
From the power analysis, we see that the device operates at 677 milliwatts. If we convert this into thermal energy and subtract the rate of heat transfer leaving the device during operation, we calculate that the device will reach its peak temperature at 96.6 seconds. The device's temperature would increase by 0.086 Celsius, which is around 0.15 degrees Fahrenheit. After the 96 seconds have passed, the increasing temperature reduces. At the peak temperature increase, the device will not overheat and will be completely operational.
We have proven that each component fits within the housing, which mounts securely within the bike handlebar, and that the camera, sensor, LEDs, and micro SD card interface properly with the microprocessor, such that when the device senses disturbances within 3 feet, it indicates the warning LED, captures images, and saves those images to the micro SD card. With the budget of everyday cyclists in mind, one of our biggest considerations was affordability. In all, the components totaled $179.07 per device. And with design streamlining and more direct product sourcing, this cost could be even less. Before reaching the masses, we plan to make CycleSafe more rugged by integrating vibration, dust, and weather resistance. With these adjustments, cost-friendly parts, and help from cycling advocates, we believe CycleSafe can make a positive impact on the safety of the biking community. Our team learned valuable lessons during this project, with many of which coming to light during the COVID-19 pandemic. Due to safety concerns, we could no longer meet during our testing and prototyping window. We also lost the ability to meet with our professors directly, and we lost access to our on-campus workspaces where we would assemble and test our device. Because we were no longer able to share components, each team member needed his or her own pieces. However, challenges with ordering and shipping resulted in changes to our project's timeline. This taught us the importance of project planning, adaptability, communication, and the value of our project resources. While all of these factors have been challenging, our team has pulled it together and grown to be better engineers.
Thank you to everyone who worked tirelessly to make this project a success. A special thanks to our incredible sponsor, Dr. Daniel Latt, and our mentor, Robert Messenger, for their help and guidance. Thank you also to Tech Launch Arizona for helping us throughout the patent process. And thank you to the Tucson Police Department for their assistance. Finally, I am so thankful to my amazing team for working together and making this a wonderful year.